Yeah. Like somebody that watches.
I don't know, but I know in Zona.
What's the Swana word? Mobility. That's not what you said. Anyway, so the reason I want to know is I was thinking of how to explain vectors on a manifold. And then I met the cashier and she told me her name, and I asked her what it meant, and she said it was watcher. Or I first misheard it. But then she went like this. And I was like, that's useful. And so if I had to define a definition for a vector, it's exactly this.
Oh.
It's an entity that watches functions. Okay. So what a vector does on a manifold, it's something that probes functions, it asks them questions, and it has a way of storing the answer. Now, the only thing you can ask a function at a point is how it changes in one direction versus how it changes in another direction versus how it changes in all possible directions. And then you keep that answer. So what a vector does effectively on a manifold, it's basically tells you what questions to ask. And you know, on a manifold of n dimensions, you're only going to ask n questions because it can only change in n possible ways. Okay, so you can view the basis, these x mu's, which actually correspond to like ddx on your chart, as the possible questions you can ask the function. It's like, how do you vary in that direction? How do you vary in this direction? How do you vary in that direction? How do you vary in this direction? Any question your vector asks the functions can be made up out of this basis. And a particular vector is then a combination of these questions. Okay, and that combination is being stored in the components of the vector. In other words, how you've combined these base questions. Okay, so a vector itself is how you store how you're going to answer the questions. Okay, so a credit to the lady at the spa for inspiring, and I think it's a nice explanation. It's basically not a vector that we think of like a pointing arrow. It's a structure that asks questions of functions on your manifold. Okay, and I hope that helps a little bit with the interpretation as things go on. Okay, so we've got vectors, we've got hopefully a better explanation so far, and then vectors are defined so far only at a point P. And what we're now trying to develop is how we connect points. And the first piece of machinery we had to get to be able to connect points is this idea of a smooth curve. Okay, and a smooth curve is a parameterized list of points. In other words, and the way we parameterize it is we define this map gamma that takes us from the real numbers or interval on the real numbers to the manifold. And it basically gives you a list of points that are hitched together. And then on that curve, we want to choose a particular vector that's going to point along the curve. Okay? And that particular vector we're going to define as the tangent vector. Okay? And the way we define the tangent vector as the special vector in the n-dimensional vector space that is equal. In other words, remember, a vector is a function watcher. It has n questions. It can ask your functions and it gives a number back. Okay, so this particular vector is the vector, yes?
So basically it acts like a locator. Can it locate to?
It can't locate. It acts, because it only is defined at one point. It acts as a probe of any function at that point. It's literally storing how the function is changing in the different possible directions. We're going to get to locators when we do curvature. There are things like that. So, in fact, very nice thought experiments that way. So we have this special vector that is basically measures how the thing is changing along the curve, okay? And the way we assign the value of that tangent vector is to say that it is basically ddt of this function. Okay, so our value that the tangent vector gives back, we can compute by taking the derivative of the function that is constructed by taking a part of the interval of the reals to the manifold and then mapping it back by any arbitrary function to the reals. Okay, so you can either go that way around, or you can have, but the result is basically you're mapping reals to reals with this composite function. Okay, and even though we do not know what f is, we define our tangent vector to have the same value as how this thing would change as we change parameter along the curve. Okay, and while that thing is abstract, we can get a very real idea of what it is when we start looking at the coordinate basis. Okay, so let's try and express our tangent vector that's abstractly to the curve, that's defined like this in terms of the coordinate basis. So the way we do that, remember we had a chart, namely the coordinates on the manifold that maps it to R3, and then we define our coordinate basis x mu to be simply this derivative of this f circle phi minus 1 map with respect to the actual base coordinates. And so what we basically did is, so on the coordinate basis vectors, with a given chart, the tangent is the curve on the manifold obtained by keeping all the coordinates except for x mu constant, right? So our coordinate basis actually gives us some curves as well. And so what we can do is, if we're given a chart, this curve gamma on M will be mapped to a curve in the coordinate basis. In other words, we start here with this curve, we take phi, which associates a coordinate with each point, and it will result in a curve in three-dimensional space, or n-dimensional space. And what we then do is, that curve is a curve like we've been working with for the rest of the class, for the beginning of this class. It's simply a set of coordinates in Cartesian n space. And so these coordinates are basically parameterized by x mu of t. Okay, so we basically use our chart to take this curve in our manifold to 3 space. And then what we have is that for all f in functions, we have our tangent watcher that always gives the result back. This is just a definition of how basically the function changes along the curve. Okay, and if we massage this thing, we take the full derivative ddt and we write it again using the chain rule as the partial derivative of f circle phi minus 1 times ddx of t, and then we can express it as dx d mu dt times the coordinate basis f of mu. Okay, so if you have a chart and you have this coordinate basis, the tangent vector simply has components of how the coordinates in R3 are changing with time, and then you multiply it with its coordinate basis itself. So it's exactly, once you have the chart, what you intuitively think of as if you were thinking of the curve, not necessarily looking on the manifold, but its map from the manifold into R3. So you're once again using the trick where you use the fact that you know that R3 or Rn is well defined and you know what a curve does there, and you use that through this very rigorous mapping method to actually define what a tangent vector is over here. Okay, so let's go on. Stuck. Okay, so the components of the tangent vector to gamma, okay, so remember you have the idea of the vector, then you have the vector expressed on the coordinate basis, and the components on the coordinate basis of a particular vector given a particular chart are just how the coordinates of that curve are changing in Rn. Okay, so we have T of u equals dx u dt, where, so for example, in 3 space, x of u would be x, y, and z, and so it would simply be how dx, dt, dy, dt, dz, dt would be the components. And they are always indicated with up indexes. Okay. So that's a tangent vector on the coordinate basis. And so what we now have, for the first time, let's introduce 2 points on a manifold. In other words, P, where we've defined everything up so far as a single point, and then we're going to have another point Q, and we're going to have P not equals to Q. Okay. And then the problem we face is the way we've defined things so far is that potentially the tangent space at P, and by tangent space I basically mean all possible vectors that you can find at P, is different from the one at Q, because nothing we have said connects the two. Okay? All we've had is that a vector is a function watcher here, and you're going to have a different function watcher over there at Q. And so the problem is we cannot determine if a tangent vector at Q is in some sense the same as a tangent vector at P. Okay, we haven't yet got the machinery to do that. We are going to develop it, but that's where it gets more subtle, right? If we're working in Rn, we could have had it, and we had just a curve in Rn, we immediately knew the intrinsic idea of a vector here, how it's related if the vector changes to a different part on the curve. We cannot do that for the manifold. We can define the vector, we can work out its components, but we cannot say if there's any intrinsic relationship between the vector at P and at Q, because we don't yet know how to do that. Okay, but there is a method, and that's what people say, that people call it parallel transport. And this is the start of developing basically what a geodesic is. And the idea is you basically transport the vector in a manner that makes minimal possible distortion. And that's still in quotes, but I'm going to make it concrete in a while. Okay, so this is sort of what's coming, is we're going to start describing how you take a vector and you transport it, and to be able to transport it you need a path. In other words, you need a curve to take it from P to Q. Okay. In normal Rn, you didn't need that. You could just take it and move the base of the vector. Here, in curved manifolds, you do need a path. And what is even more interesting is depends how the vector is moved, it depends on a path. Only in flat space, if you take a vector at one point, you move it to a different point, does it have an unambiguous meaning. On a circle, suppose you were to take a vector, and you can actually do this. You move it along the circle with a certain rule, you move it along another circle with a certain rule, and you move it back. You're not going to get the same vector, it's going to change. And how you do that systematically is what we're going to start looking at now. Okay, so the result depends on the choice of the curve for non-flat spaces. Okay, so now we're going to systematically start building up vectors at more than one spot. So the simplest definition of a group of vectors is we call it a tangent field. Okay, And what a tangent field is, it's simply assign a vector at a whole series of points, okay, for every point in M. Okay, so all this basically says is you're going to look at every single point in your manifold, and all you know about every single point in the manifold is that they all are in one of these open sets, and they also therefore guaranteed to have a chart to Rn, okay? And at every single point, you're going to assign a vector at that point, okay? In other words, what you're going to do, for example, is specify the coordinates on terms of the basis, okay? And a vector field is basically the container in which we store all these vectors at distinct points. We haven't yet joined them together. Okay, what we're now going to do is start saying what the conditions are if a vector varies smoothly over a manifold. Okay, so even though if you have vector spaces Vp and Vq, where p is not equals to q, they are in fact different vector spaces. You can't view them as being one vector space. They each have dimensionality n. They each have their own bases that can vary. What you still can do is you can define what it means if a V varies smoothly over M. Okay? And the way you do that is you look at what V spits out. Right? Remember, V is a questioner. It takes the function and it asks questions and it gives you a real value back. So you can say V varies smoothly if the answer it gives you back doesn't vary smoothly. Okay, so you judge V by its output, effectively. Okay, so the way we do it is we say the vector field at the particular point applied to a function f is going to give you a real number. Okay, and that number is basically going to be a real number for every single point in the manifold. Okay, and to think about it over here, let's have a look at this example. So for example, let's look at a very coarse graining. Suppose we have like a parabolic roof or something. Our tangent space, say at that point, and at that point, and at that point, they're all different, right? Our tangent space is basically the sheet or the thing that has contact there, the flat sheet of paper that has contact there and has vectors that give us its direction. Okay, so this white thing is a two-dimensional surface. Therefore, its tangent space will also have two dimensions. And the basis of the tangent space will therefore point one, say, in that direction and one in that direction. Okay. And so any vector at that point is basically a combination of those two basis vectors. But then you have this another point over here, say, call that Q. It has a different tangent space. Okay, it once again has two basis vectors because that's a guaranteed, but they're completely unrelated to that point over there. Okay, and so what we do when we describe a tangent field is we literally say we want to make these tangent spaces smaller and smaller and smaller so we can get a better and better local tangent space approximation, and we can go even further. And our requirement is that the output of the vector at this point, when you compare it to the output of the vector at that point, varies smoothly. In other words, there are no jumps in it. And if we can get a collection of vectors that basically gives us that, then we have a smooth tangent space. So it's a very abstract idea, but this picture basically illustrates what we are trying to do. We are at each point wanting to assign a particular vector, okay, such that when you move to the next tangent space, the function or the answer it spits out for every single function, which is always a number, doesn't make jumps in it and vary smoothly. Okay, so now that's a nice abstract idea. Let's see what it means for our components, right? So if we say V is a smooth tangent field, okay, what that means is for all f, okay, for any single function it watches, you basically have the map of M to R, okay, and the function V of f is also smooth. Okay, that's the only requirement of a vector field, is that its answers it gives out when you apply it to absolutely any function mustn't have jumps into it. Then you have a smooth tangent field. Okay, what that means is that suppose you have your vector and you have your coordinate basis fields and they are smooth. In other words, derivatives on your vector of functions on your Rn are smooth. Then V is smooth is the same as saying its components on the coordinate basis are smooth. So once again, you have this abstract idea of vector. For the practical means of calculation, it's going to be the actual components on the particular coordinate basis in Rn. Those are the things you're going to store. And as long as those are smooth, you have a smooth vector field. Okay, because the basis is always smooth the way it's defined, and if the components are smooth, then the combination, the answer it spits out will always vary smoothly. Okay, and so remember we have the vector, we express it as these components times these basis vectors, and as long as the components there are smooth, we're fine. Okay, so that's a vector on the tangent field. That's how we're starting to develop the ideas of how you connect them closely together. Questions now before I go on? No, not yet. You're brave. Okay, so the next thing we're going to do is have an idea of a displacement. Okay, so when we look at manifolds, vectors and displacements are distinct. Okay, very often when we do physics, we say an infinitesimal displacement is simply a point plus a little vector times delta pointing along that way. Just ditch that for now, okay? Because it doesn't work, right? Because the problem on a manifold is, suppose you have my coffee cup, and suppose I start over, is there a pen somewhere that I can write on my coffee cup? Oh no, I want to, pass me that, throw me that thing behind. Kokie, yeah. Good. Okay, so what we want to do is, suppose in normal three-dimensional physics, suppose we have my coffee cup, there's a point. Okay, so in what we usually would do is we would say we start at the point and then we'd have a displacement delta times a vector. But you can see what the problem is, right? The vector is going to take me off the manifold if I just do it that way. Okay, so we want a different way to define displacement in a fashion that, suppose I start at this point and I say I have an infinitesimal displacement, then I move, but I move not along a vector, I move in a fashion that basically keeps me in the manifold. Okay, so moving on a...
So basically we're taking a closed contour or different...
We want to stick on the manifold. It's not a contour. It's, okay, so far we don't have the idea of a contour. We've got a curve, we've got a point, we've got vectors, and we've got a chart. So you've got to make up what you're doing in terms of those things. Or you've got to define a new concept that you define well. Okay, but all I wanted to illustrate is the basic problem of a displacement can no longer be what you've done in basic physics, because a vector doesn't keep you in the manifold itself. And so the way we start structuring displacements is basically, look what I've done, is I've taken this point and I've put it to another point on the manifold itself. So effectively, a displacement is a rule of mapping the manifold onto itself. Okay, so we're going to, that idea generalizes, and that's what we're going to do now, okay? And so what we do is to define a displacement, sorry, is we introduce this idea of a diffeomorphism. So we're going to define a one-parameter group of diffeomorphisms in the following way. So diffeomorphism is basically this fact that you're taking one point on the manifold and you're mapping it to another point on the manifold. Okay, in some sense, it's simpler than the idea of a vector. And so the way we define that is we say it's phi of t is a C infinity map that maps R cross M back onto M. Okay, so it's a clever structure. So what we do is we say, we don't tell you what the map is, we're just working with the abstract idea of the map. And what it does, one, you need M, which is my coffee cup. Two, you need how far you are moving. So you need a measure of the distance of your displacement. And that's where the R comes in, okay? And then you're going back onto the same manifold. Okay, so that's literally what I've done here with my coffee cup. And so you can do that not just for one point, but you can do it for a whole batch. And then you've basically got a diffeomorphism of my coffee cup. Okay, suppose I have the rule that I take everything here and I move it so far, and then I have another set of points that have basically been rotated on my coffee cup. So that's the idea of that diffeomorphism. And so the conditions on this diffeomorphism is such that if you fix t in R, which is basically the size of my displacement, okay, then phi of t for a fixed t is simply a map of the manifold to itself. Okay, so in this coffee cup example, I'm basically saying I fix t, so suppose I make it, say, 0.5. I want to move every single point on this vertical line on my coffee cup 0.5 to the right. Okay, so that thing is a diffeomorphism. And for all s and t in R, you have the following conditions of your diffeomorphism, because you want the idea of additive distance. So what this thing is, it's basically if you take one diffeomorphism that takes all these points and moves them a distance, say 0.1 to the right. I think is it your right or left?
Your right.
It's your right. Okay. If you move it 0.1 to the right, okay, and then you say you want to apply this diffeomorphism again, say a 0.2, say S is then 0.2, then you move it another 0.2 further on. You want the idea that two of these movements basically correspond to one movement where you've moved both the sum of the two directions. So here I'm building in that the idea of distance that is additive is just the normal one that you have. Okay, so that's how we defining displacement. Very different from whereas physics you have displacement and vectors connected. Here they are for now totally different ideas. Okay.
So t and s can't be equal to each other, or they can?
They can.
They can.
Suppose, for example, I move all these vectors like 0.5. So here let me say this is t. Okay, so this is the same t, for example, for all of those. And then I say I want to move it again. And I call that S, that basically moves everything like that. There my T and S are the same. And the condition of my map is that I can either go a little bit t and then a little bit s, or I can go t plus s and I get to the same answer.
Yeah.
Okay, so I'm going to have a very decorated coffee cup once I'm done. Okay, so another thing is, if you don't go anywhere, right, then it's just the identity map. Then you've just got the manifold back onto where it is. And this idea is very, very powerful.
Can I ask something?
Yes.
So if we say we have this movement t, and we take the inverse of this movement t, and we apply them both, are we going to then move forward and then move back, or is the inverse of phi referring you going back to, is this phi the same phi we had on like this sketch from here to here, or is
No,
okay.
no. This, look, whenever I define something, look at where it,
Okay.
the symbol doesn't matter, where it's mapping from and to, and what the conditions on the mapping are in the same box matters. Okay, so, but your rest of your question is very good. Suppose you have one diffeomorphism that takes it a step t, okay, and then you have s, but s is equals to minus t. Look, it's mapping from r, so r can be positive and negative. If s is equals to minus t, then what you're going to basically do is you're first going to go there, and then, so that's s, okay. No, so that's t, sorry. So it's first going to take a step t, and then it's going to go, if s equals to minus t, it's going to start over here, and it's going to go back, okay? And what you're then going to get is that you actually haven't moved anywhere, because then you have phi of s of t plus minus t is phi of 0, and that's your identity map. Okay, so nice question. So basically, your identity map is going nowhere, but the idea of distance is coming in by this property where you add it together.
And then is the step t that you take, is it unique in the sense that you can just say that, or can you apply it like with a bow that you travel to get to that same point? So is it unique, or can you go for a walk and then end up at the same point?
We haven't said that yet. Okay, so all we've said is that if you have this thing that takes every single point to another point, and all the nastiness is actually hidden up in this map over there, how are you going, whether you're going on straight lines like this, or whether in your case you've started here and you take a step t and you end up at that point, and then you take this point over here and you do that, all that type of thing is hidden in phi. Okay.
So the path does not matter. We're only looking at the final displacement from point to point, but does not matter what path.
We haven't specified the path. Okay. And eventually it does matter. And eventually we learn a lot from that. But so far, with our definition, we haven't specified anything about the path. And also, to try and avoid all this funny concoctions that is possible, we're eventually going to work only with small steps.
Yeah.
And then it's effectively linear. Okay. But we haven't done that either yet. We've just specified the idea of what this diffeomorphism does. Okay, so what now we're going to do is, and here is, we know in physics that our vectors are associated with displacements. We want to find a connection between the idea of the displacement and the vector, and this is how we're basically going to do it. Okay, so we're going to say for a fixed P in M, okay, we are going to examine everywhere where this diffeomorphism maps that particular point. Okay, so remember our diffeomorphism takes every single element in M and maps it to another one if you tell it how far. Okay, so, but to associate a vector with a displacement, we're going to look, remember vectors so far are only focusing at one point. We're going to pick a particular point. And if you pick at a particular point, you basically fix it to one element in M. Okay? And then the only thing that changes is how far. Okay? So then we're going to study this thing. So this phi of t of p is basically a map from how far, which is r, to the manifold. And what is this, if you look simply at what you're doing?
Going from that line to manifold.
Yes, it is your curve. It is our definition of a curve. So we are, for a particular point, we are restricting the discussion to what this diffeomorphism does with that point, and by doing that, we've basically looking at one line, which could be very curvy. Okay. And now I just want to finish this bottom and then we can go. So that line that's associated with the diffeomorphism we call the orbit of phi of t. So for example, this random curvy curve that you've described over here, that is the orbit of phi of t of that particular point.
So that is like the path.
That is the path.
Okay.
Okay. And that orbit passes through P at its starting point. And we can then go on and define the vector V at P to be tangent to this curve. Okay. So then we have a relationship between the diffeomorphism, in fact the path, in some sense the map of the manifold to itself, and the instantaneous vector at that point, okay, is simply the tangent to the curve we define by looking at what the diffeomorphism does to one point. Okay, I'm going to stop there and then go on next time. Or not next time, I'm going to do the pulsars next time and then go on next Monday. But yeah, your pictures are valuable to me. Okay, do these things, write them down that you get a feeling for it. And then eventually we're going to actually see how powerful it becomes. Okay, thank you very much.